Our topic today is Gram-Schmidt procedure of orthogonalization. So uh, we will see what actually we get when we apply this Gram-Schmidt procedure and where we can use it. Suppose you have a set of m non-orthogonal signals. So you have a set of m non-orthogonal signals, and you want to convert or you want to form another set of n orthonormal signals, orthonormal signals, right? When we say orthonormal signals, the signals are orthogonal and they are normalized. Their energy is unity. So we would apply the Gram-Schmidt procedure to this set, which contains m number of waveforms, m number of signals, or we can say m number of signals as m of t, a set of m number of signals. We can write here that our m varies from 1 to capital M, right? So we have a set of m number of signals, and we are going to form another set of n number of signals, right? N number of signals, and in this set we would have n waveforms, which we can represent psi n of t. We would have capital N number of waveforms, and all those waveforms or all those signals would be orthonormal, right? So basically the Gram-Schmidt procedure is applied to this set to convert another set of signals which contains n number of signal waveforms, and those signal waveforms are orthonormal. Keep in mind this capital N is less than or equal to n. So it is either less than or equal to m. So it means both sets may have same number of waveforms. Here we have non-orthogonal waveforms, while this set non-orthogonal waveforms, while in this set we have orthogonal waveforms or orthonormal signals. So you are already familiar with the significance of orthogonal signals. We prefer to transmit orthogonal signals specifically in wireless communication, and the reason for orthogonal signal transmission of orthogonal signal is that we can easily distinguish those signals at the receiving end. So orthogonal signals is an important class of signals which is most commonly used in wireless communication. So we assume that our signal of non-orthogonal signal set which contains Sm of t, and this S non-orthogonal, we have a non-orthogonal signal set and it contains Sm of t signal waveforms. Any signal can be considered as Sm, and this M is from 1 to capital M. All these signals are non-orthogonal. And they have some energy. So usually when we have a set of signals, we can represent the whole set using this notation, that okay, this is a set of signals which has many waveforms, and those waveforms are non-orthogonal. After applying Gram-Schmidt procedure, we would get another set. In which we would have n number of waveforms, and this n is less than or equal to m. We would have n number of waveforms, and all those waveforms would be orthonormal. So any of those waveforms can be represented in this form. This is the set of those waveforms, where I can say that my small n varies from 1 to capital N. So we are going to apply Gram-Schmidt procedure to get this new set, which is here, this new set which has some important orthonormal signals. Later on we would see that each of these signals, each SM of t can be represented as a linear combination of this set, right? Orthonormal signal set. So let's try to apply this procedure on m number of non-orthogonal sets. First, in the first part, we would like to cover the theory, and then we would see with the help of an example to how we can apply Gram-Schmidt procedure. So let's see how we can convert a set of non-orthogonal waveforms into a set of orthonormal waveforms, right? So let's try this procedure step by step. So in the first, I would like to write here step number 1, right? So in step number 1 of this conversion process, what we do, we choose any signal S1 of t from that set M. From set M, we choose just any random, the first one. We can choose any one, right? We choose, it's not necessary, not specifically some specific waveforms, but you choose any one. The first you choose is S1 of t. So we choose a waveform, a signal from this set, and we call it S1 of t. Now we would like to get the first orthonormal signal from this S1 of t, and this S1 of t has energy. Suppose this S1 of t has energy E1, right? Suppose it has an energy E1. So how we can write, we can convert it into, first of all we have to convert it, we convert it into a unit energy signal. So to convert it into a unit energy signal, the procedure, the easiest, it's not only for this one, to convert it any signal into a unit energy signal, just divide that particular signal by the square root of its energy. Here we have the energy E1, so we are dividing S1 by the square root of E1. Now we call this one the first signal which we get, this one as the first orthonormal signal. We say this is our first orthonormal signal. So our psi1 is now we have assumed that this is our first orthonormal signal, right? Now we can prove here at this point that the energy of psi1 is unity. We can always prove that the energy of psi1 is unity, and to find the energy is the easiest ways to just integrate its square, right? This is how we find the energy of a signal. So if you solve this integral, you will get 1, right? So this is our first orthonormal orthonormal signal, which we form this signal from S1. So in step number 1 we get psi 1 of t. Now in step number 2 we have to take another waveform. So I would like step number 2. Now in step 2 what we can do, we can choose another waveform and we call it S2 of t, another waveform from that set M. So this is a second waveform, S2 of t, and of course it has its energy E2, right? Well, we will not use the energy of this signal, but suppose it has energy E2. So we have the S2 of t. Now we already have a signal, a waveform. We already have an orthonormal basis function, right? And we said that its energy is unity. We can verify it right now. Now to find out what we have to do, when we select S2 of t, the second waveform, second non-orthogonal waveform from that set, we find the projection. We find the projection. I would like projection of S2. We find the projection of S2 of t onto psi 1, because this is a non-orthogonal signal, so it has a projection. If it has any projection on psi 1, we have to find it out, and then we would like to subtract that projection from S2, right? So what actually in the step number 2, we have to find the projection of S2 over psi 1 of t, and that projection is actually the integral of this product, S2 of t multiplied by psi 1 of t. So and if we integrate it from minus infinity to plus infinity, if we integrate it, actually this integral gives us the projection of S2 over psi 1, and we call it C12, the projection of the signal. Now this first subscript is used. The first subscript, keep in mind, in this C12, it's a definite integral. It's a definite integral, right? It's a definite integral with limits. So you would get a number. You would get some value here, some real value, some scalar. So now this, when we say C12 in this notation, the first subscript is for this basis function. So the first subscript actually is the projection onto psi 1. So the first subscript 1 is for basis function, and the second subscript, this one, this is to represent the signal S2. We have chosen the second signal. So we are this C12 is the projection of S2 of t, the second signal, over the first basis function, right? Now when we find out this projection, when we find out this projection, it means S2, because S2 is non-orthogonal, right? We already said that S2 is non-orthogonal. So when we find the projection of S2 over psi 1, then we can subtract that projection from S2. What we have to do, we would subtract that projection. Now in the next step, we have to subtract that projection. Now C12 is a scalar, right? C12 is a scalar which shows the projection of S2 over psi 1, right? Now we would like to subtract this projection, so from S2. So if I subtract the projection, because this is the now C12 psi 1 of t, this is actually the projection of S2, this factor, this scalar, represent the projection of S2 over psi 1, right? Over psi 1. So we want to subtract this projection from the signal, and we would call it a signal D2. We call it a signal D2. So this is our new signal. This is our new signal, and this D2 of t, this D2 of t will be orthogonal. It will be orthogonal to psi 1 of t. Psi 1 of t. Why it will be orthogonal to psi 1 of t? Because this is actually S2, and the projection of S2 over psi 1 is already subtracted, so you have no projection of this signal D2 of t over psi 1. Let me clarify this one graphically. Let me clarify this graphically. Now we know that if we have psi 1 of t, we have psi 1 of t which we found in step number 1. So that is our first orthonormal basis function, orthonormal signal, our first orthonormal signal, and we can use that orthonormal signal to represent this axis. Now the other signal, suppose our another signal S2 is a vector. This is the vector of S2, right? And it has some projection. It has some projection over psi 1, which is this one, right? This is the projection. It has the projection over psi 1, which is given here. Now this projection, which this length, we have found this length C12. So C12 times psi 1 of t, this vector. Now this is a vector. C12 times psi 1 of t is a vector, and this vector is actually a part of S2, a vector S2, and this is the projection. This is the projection of S2 over psi 1. What we do, we subtract this projection. So if we subtract this projection, if we subtract this projection from S2, then only this projection, this will be, we are left with this one, this vector only, because this S2 has two rectangular components, this one and this one. We already subtract from S2, this projection, so we are left with only this one, and this is perpendicular, this is orthogonal to psi 1. So that is why this is actually this vector. This vector is for D2. This vector is for D2. So we are getting D2 of t. D2 of t, which is S2 of t minus C12 psi 1 of t. Right? So the projection we already subtracted the projection, this projection from S2 of t. So this D2 of t, is orthogonal to psi 1. So we can, now this is orthogonal to psi 1. If it is orthogonal, then we can, it means we can find our second orthonormal signal psi 2 of t from D2 of t, because we already found an orthogonal signal. So if we divide this signal by the square root of its energy, suppose I mention it by ED2, the square root of its energy, the resultant signal would be orthonormal, because we already said that it is orthogonal to psi 1 D2, and when the energy is divided by square root of its energy, the energy of this resultant signal is unity. Its energy is unity. So when the energy is unity, we can call it, this is the property of orthonormal signal. Its energy is unity, it's orthogonal to other signals, right? So we found another basis function, psi 2 of t, right? Psi 2 of t, which is now orthogonal to psi 1. Now we can continue this procedure. Let me do it to find out psi 3 of t. So now what we have done till now, if you see, we selected S1 of t, the non-orthogonal signal from M non-orthogonal signals. We selected first one, and we found psi 1 of t from this signal. Then we selected another waveform, another non-orthogonal waveform, and we found psi 2 of t from this non-orthogonal waveform, right? Now we can choose. Now we have used two waveforms, and we found two orthonormal signals. So in this set we have two orthonormal signals. Here we have used only two of them. Now we would choose the third one. We would choose the third one, S3 of t, right? S3 of t. We choose the third one, and we try to find out our third signal, third orthonormal signal. So when we choose S3, we already, now keep in mind, we already have two basis functions, psi 1 of t and psi 2 of t in our set, right? So these two are already there. When we choose S3 of t, first of all we have to find out the projection of S3. We need to find out the projection of S3 over psi 1 and psi 2. And we have to subtract those projections from S3. So when we subtract those projections from S3, we would get a signal. That signal would be orthogonal to these two basis functions. And then we can use that one to form another psi 3 of t, right? Psi 3 of t. So this is the procedure we have to follow. So I would like directly here now my d3 of t. First of all, now let me repeat, S3 of t. From S3 of t, we need to find C13, which is the projection of S3 over psi 1, and we also need to find C23, which is the projection of the third signal over second orthonormal waveform. Once we find this C13 and C23, then we can find our D3, the signal, or this D3 of t. And D3 of t would be the signal S3 of t minus C13 psi 1 of t minus C23 psi 2 of t. So this would be S3 of t, this D3 of t would be the signal which would be orthogonal to psi 1 and psi 2, right? And the next step is easier. What we have to do, we need to divide D3 of t by the square root of its energy. Suppose the energy is represented by sub D3, so this would give you psi 3 of t, the third orthonormal signal, right? This would give you the third orthonormal signal. we have to continue this process, right? We have to continue this process, and if we continue this process, uh, uh, until all the non-orthogonal signal sets, all the waveforms of non-orthogonal signal sets are utilized, until all of them are exhausted. So we till the end, we have to continue it till the end. In general, if you summarize this, what we are actually doing, we are trying to find out the image of the signal. First of all, we are trying to find out the image of the signal, which I can write the image of the kth signal over the ith basis, ith orthonormal signal, and we try to find out this image, which is sk of t psi I of t dt. We used to find out this image, the image of the signal. We choose the signal sk of t from the non-orthogonal signal set, and then we find this image, right? We find this image. So in general, Cik, we can write now a generalized expression for Cik, where we can say that our I is from 1 2 up to k minus 1, right? So Cik give us the image of image of the kth signal over the ith basis function. So this subscript is for the signal, and this subscript, the first one subscript, is for the basis function. So we can write this generalized expression for Cik, right? We can compute it this way. We can also write the generalized expression for our dk. We can say dk of t, the signal dk of t. We can write the generalized expression for this dk of t. And what actually we do when we select a kth signal from the set, we subtract all the projections. We subtract all the projections from this signal to find out dk of t. So the projection, all the projections, we can just write it for all the orthonormal basis functions. We try to find out Cik psi I of t. So for all I, or we can say for I 1 to k minus 1, because we have we say that it is when we choose the kth signal, then the k minus 1 basis functions, we already have formed these basis functions, right? So try to understand this expression. This is Cik psi I. This is the image. This one is the image of the kth signal over the ith basis function. So for all I, or for I 1 to k minus 1, you have to subtract all the images, all the projections, all those projections from sk to find out dk, right? So this is a generalized expression for our dk of t. We can also write the generalized expression for our psi k of t, psi k of t, the orthonormal basis function, which is usually which is from dk of t, and we divide this dk of t by its energy of E dk, right? We divide when we find this dk, we can just use it to generate psi k, right? So this is a generalized expression for our psi k. Now based on that procedure, you can test it for d2, for example. If k is equal to 2, so d2, we just did that one, so put 2 over here, so you would get d2, 2 over here instead of k, right? So when you have 2 here, you would have 2 here, and you would have for I1 2, just k minus 1, k is 2, so 2 minus 1 is 1, right? So you have only k is 2, so 2 here, and you have I, the value of I is only 1, I 1 to 1 means just 1, so you are subtracting C1 to psi1 off. So when k is equal to 2, you are subtracting C1 to psi1 of 2. So when you choose the second basis function, you have only the second signal, you only have the first basis function psi1 of t, right? So you subtract that one from S2. Similarly, you just replace it with k3, and then here in this summation you would have 2 terms. So with k4 you would have 3 terms here in this summation, and so on. You can extend it to any number of k. So this is how you find the orthonormal signal from non-orthogonal signal set. Now once you find the set, the orthonormal signal set, which has, once you find this orthonormal signal set, which has which has n number of waveforms, and we said that this n is less than or equal to m, right? This is less than or equal to m. Now what we can do, we can now easily represent. Now if you see, what do you have? You have 2 sets. In one set you have all the non-orthogonal signals, right? And now you have another set, psi n of t, where you have all the orthonormal signals, 1 to capital N, right? So you have 2 sets now. These are all the non-orthogonal signals. These are all the non-orthogonal signals. And here you have orthonormal signals. Here you have orthonormal signals, right? Here you have orthonormal signals. What we can do, we can represent each Sm of t. We can represent each Sm of t as a linear combination, of this, as a linear combination of psi n of t. And when we say linear combination of psi n of t for n 1 to capital N, when we say linear combination of psi 1 of t, then we have something here, some scalar over here, and that scalar would be represented by Sm. For the mth signal, this is the scalar. So you can represent each waveform as a linear combination, as a summation of this non-orthogonal, these orthonormal waveforms. And here our m, this m is from 1 to capital M. Should know this. And our n, of course, our n varies from 1 to capital M, right? So we can represent now. We can represent our waveform. We can represent each Sm of t, we can represent each Sm of t as a summation of psi n of t, and this is for all n 1 to capital N, right? For n 1 to capital N. So we can represent it this summation. This is true for all values of m. So S1 of t, S2 of t, any of that can be represented as a linear combination of these orthonormal signals. And what is this scalar? How you can find this scalar? We just discussed it above. We can find this scalar S n m. The image of the mth signal over the nth basis function, we can always find this by finding out this projection Sm of t over onto psi n of t. So if you find this, usually our signal is only from 0 to t, so our limit from minus infinity plus infinity changes to from 0 to t. So this is the value of that scalar, or the projection over of m, the projection of Sm of t over psi n. So this is how we find this scalar, and of course the energy of the mth signal, you can always find the energy of the mth signal by integrating the square of the signal, right? The square of the signal. This is one way. Either you can integrate, you can write this energy in this form, or you can also write the same energy as a summation. Once you find these scalars, you can always find the energy by using the sum of the squares of all these values for all n. Just take the sum of the squares of all these. So the energy is either you can find from this expression as well as from these scalars as scalar values. Now once we find out these scalar values, we can write our signal in the vector form. So our Sm of t, which can be written as a linear combination, as a summation of psi n of t for n1 to capital N, and we have of course this scalar. We can write our Sm of t as a linear combination of orthonormal signals, and we can write it in the vector form by just using those values S2m and S last value would be Sm. These are the those scalar values. Actually it tells us that our signal Sm of t, it is n-dimensional signal. So we can draw it in n-dimensional Euclidean space, right? So our signal is n-dimensional signal. Our signal is n-dimensional signal. So our Sm of t is actually n-dimensional signals, and all these components are there. You can use these to represent Sm of t as a single point in n-dimensional Euclidean space. So if this n is 2, we have a two-dimensional Euclidean space, and it means we have psi 1 of t and psi 2 of t, and your signal Sm of t would be a point in this space. It's somewhere here, somewhere here, somewhere here. These are all those non-orthogonal signals. It can be, we can represent all those non-orthogonal signals here. So these are just points, and if n is 3, then we have 3-dimensional Euclidean space, and so on. We have 4-dimensional. Any number of n is possible. You can extend this concept to n-dimensional signal space or n-dimensional Euclidean space. So this is the whole theory, the whole concept of Gram-Schmidt procedure, and what we achieve by applying that Gram-Schmidt procedure, that we converted the m non-orthogonal waveforms. We not actually converted, we just constructed another set of n orthonormal signals, n orthonormal signals from this m non-orthogonal signal set. Right, we just constructed this new set, and then we saw that each of the waveforms Sm of t from this set can be represented as a linear combination of this psi n of t, as a linear combination of these orthonormal signals.